Welcome back to our third installment of our story From the Ancient Greeks to Isaac Newton, Early Astronomers, the Birth of Science, and the Origins of Calculus. Today I'd like to start off by counting down the top 4 highlights from the first 2 presentations. Starting off with number 4, Aristarchus measures the angle beta between the Sun and the Moon when the Moon is half full. He finds it to be 87 degrees. He is able to deduce that the angle alpha is 90 degrees. How? He reasons that when the moon is half full, it's halfway between a full moon, when that angle is 0 degrees, and a new moon, when that angle is 180 degrees. He wants to find the ratio of the distance s to the Sun to the distance m to the Moon. Using the geometry of right triangles, he concludes that the Sun is 19 times farther away from us than the Moon is. Also, he knows that their angular diameters are equal when viewed from Earth. Therefore, the Sun must be 19 times larger than the Moon. So the Sun is huge. Perhaps because of this, Aristarchus proposes that the Sun is the center of the universe, but virtually no one pays any attention to him. Number 3. Eratosthenes takes note of a shadow cast by the Sun at noon on the day of the summer solstice in northern Egypt, in the city of Alexandria. He knows that at that very moment, at a specific spot in southern Egypt, the Sun is directly overhead and casts no shadow. He also knows that the distance between the 2 locations is 5,000 stadia. Using the geometry of Euclid, he not only proves that the Earth is round, he produces an estimate of the Earth's circumference, which is off by perhaps only 1 to 2%. Number 2. Ptolemy writes his classic treatise on astronomy, the Almagest, and thereby provides the world with the final version of the ancient Greeks' geocentric model of the universe. It features epicycles embedded in each planet's orbit in order to account for their episodes of apparent retrograde motion. Ptolemy's model works quite well at predicting the motions of the planets, and for 13 centuries, nobody seriously challenges it until Copernicus comes along. Which brings us to number 1, Copernicus and his heliocentric model of the universe. The appeal of the Copernican model lies in its simplicity. It eliminates the need for epicycles. Furthermore, his model suggests the possibility of a mathematical relationship between each planet's orbital period and its distance from the Sun. Even so, for various reasons, his model remained controversial for almost a century. As a predictive model, it was not yet any better than Ptolemy's model. As we shall see, it had a flaw that could only be corrected when better data became available. At this point, I would like to formally introduce the stars of our show. All of them are giants of the scientific revolution. You have already been introduced to Copernicus, of course, but here he is leading us off. He hails from Prussia in the Kingdom of Poland. From Denmark, we have Tycho Brahe, or Tycho for short. Then, representing Italy, the great Galileo. From Germany, we have Mr. Johannes Kepler. And finally, representing the University of Cambridge and jolly old England, Sir Isaac Newton. Our story continues with Tycho. Tycho was working before the invention of the telescope. He was using instruments such as the sextant and the quadrant to measure the ever-changing angles between planets and the fixed stars. And he was making those measurements night after night after night. Now, Tycho could apparently be a bit of a hothead, especially in his younger days. While at university, he got into an argument with a fellow student. This led to a duel in which Tycho lost a large portion of his nose. It was said that for the rest of his life, he wore a prosthetic nose made of gold and silver. Tycho's reputation as a brilliant astronomer steadily grew, and he soon became known all over Europe. In order to entice Tycho to remain in Denmark to continue his work, the Danish king decided to build him a castle on a private island, complete with a state-of-the-art observatory. Tycho was continually improving his instruments in the pursuit of greater and greater accuracy. One of his quadrants was so large it nearly filled an entire room. Tycho had a passion for making voluminous and meticulous observations, which he compiled over 20 years of work. Tycho was not entirely happy with either the Copernican or the Ptolemaic model. He proposed a hybrid model that he felt combined the best elements of each. In his geo-heliocentric model, the Sun and the Moon orbit the Earth, while the other planets orbit the Sun. So now there were three distinct competing models, and they became the subject of intense debate. You might wonder how this debate was carried out. As we just saw, the astronomers involved were spread out all over Europe. Let's go back to our timeline. Notice now that the printing press was invented in 1436. Am I suggesting that the printing press had something to do with the scientific revolution? Absolutely. These scientists were writing books and publishing books and sharing printed copies with their fellow scientists all over Europe. Scientists could then read about other theories in detail. And as you might imagine, they started writing letters back and forth. The point is that science works best when ideas can be shared and compared and debated freely and tested by others. That's how science becomes a self-correcting enterprise. Anyway, getting back to Tycho, he had reasons for favoring his geo-heliocentric model.
For one thing, he believed the Earth to be too big and sluggish to move at all, let alone rotate or revolve around the Sun. He could not imagine a force strong enough to move it. This perspective goes back to Aristotle, who argued that objects on Earth always tend to come to rest unless a force is continually applied to them. In contrast, according to Aristotle and his followers, the heavens were composed of ether, an element not found on Earth. From the word ether, we get the adjective ethereal, meaning extremely light and delicate. It was the light and delicate nature of the ether that permitted the rapid motion of the heavenly bodies. The mistake here, of course, was the assumption that matter found on Earth is completely different from the matter composing the heavens. Also wrong was the assumption that the laws governing motion on Earth are not the same as the laws governing motion in outer space. This is the big mistake that the scientific revolution will eventually correct, but we're not there yet. What Aristotle and Tycho and others did not realize is that frictional forces are encountered everywhere on Earth and always tend to oppose motion. In contrast, frictional forces are essentially absent in outer space. but the laws of physics themselves and the elements that make up matter are all the same everywhere.
After a new king came to power in Denmark, support for Tycho's work declined until it became apparent to Tycho that he wasn't welcome there any longer. He accepted an invitation from the Holy Roman Emperor to become the official astronomer of the imperial court in Prague. As it happened, Kepler was already working there, and the two began to collaborate. However, they disagreed on many things, including the correct model of the universe. Kepler requested access to Tycho's data, but Tycho refused him. At this point, I want to go back in time a few years and pick up the story of Kepler. Before he met Tycho, Kepler had already committed himself to the Copernican model. As it turned out, he chose the right model, but perhaps for the wrong reasons. His writings make clear that he favored a heliocentric model largely for religious and philosophical reasons. He was convinced that God's plan for the universe would be based on the abstract perfection of geometric objects. His guiding principles here represented a sort of geometrical mysticism. I'm going to show you what I mean, but first, I want you to understand the state of Kepler's understanding of the solar system. In those days, it was not possible to measure the absolute distances from the Sun to the planets. However, if you assumed that the Copernican model was correct, as Kepler did, it was possible to estimate their relative distances. Let me show you how this works. We'll use Mars as an example. First of all, when astronomers back then talked about the location of planets, it was always in relation to the fixed stars. Here I am showing you the direction of Gemini as a reference direction. I could have picked any other constellation. This is just one among many that we could choose from. In any case, as you can imagine, most of the time, Earth and Mars are going to have very different angular coordinates relative to the Sun and this reference direction. However, remember that Earth travels faster than Mars, so sooner or later it's going to catch up to Mars. When that happens and Mars is directly opposite from the Sun relative to Earth, we say that Mars is in opposition. This event happens roughly once every 780 days. In other words, after one full cycle of 780 days, Mars will be in opposition once again. Notice that Earth is now in a different location, but that's simply because Mars' period is not an integral multiple of Earth's period. The point is that whenever Mars is in opposition to Earth, the angle between the two, relative to the Sun, is 0 degrees. Now, if we go forward in time 1/2 cycle, or 390 days, Mars is directly behind the Sun, and so the angle between Mars and Earth, relative to the Sun, is now 180 degrees. You may see where I'm going with this. After another quarter cycle, you can deduce that the angle between Mars and Earth relative to the Sun will now be 90 degrees, and you have a right triangle. As we have seen, right triangles are very useful whenever you can find them. And hooray for Pythagoras. All you have to do now is measure the angle theta, and remembering that our goal here was to find the relative distance from the Sun to Mars compared to the distance from the Sun to Earth, we want to find their ratio. That ratio is simply the tangent of theta, and using this technique for the other planets, you can determine the ratios between the distances from the Sun to any two planets. These are the 5 Platonic solids. A Platonic solid is a three-dimensional object with flat surfaces, such that all surfaces are identical, regular polygons. They are somewhat mysterious. Why are there only 5? The first 3 have 4 sides, 6 sides, and 8 sides, respectively. The next one has 12 sides. Why isn't there one with 10 sides? And then there's the last one, which, for no apparent reason, has 20 sides, and that's it. To someone who is enthralled by geometry, as Kepler obviously was, the Platonic solids would be particularly alluring. So, what did he do with them? Remember once more that at this point, for Kepler, each orbit defined a circle of a particular radius. Now take any pair of adjacent circles, and Kepler could give you a pretty good estimate of the ratio of their radii. The problem for Kepler was that these ratios, representing the gaps between the orbits, varied greatly. This irregularity puzzled him. It bothered him. He wanted an explanation for it, an explanation that would demonstrate God's genius. He struggled with the problem. Eventually, Kepler came up with a very creative idea. What do you get if you rotate a circle around one of its diameters? You get a sphere. So now Kepler is thinking, okay, so each orbit defines a sphere of a particular radius. Now he only knows of 6 planets, and therefore there are 5 gaps between these 6 spheres now. Well, he has 5 Platonic solids at hand, and so he decides to fill those gaps with each of the 5 Platonic solids. Kepler published these ideas 4 years before he started working with Tycho. Let me show you in greater detail what he was doing. The smaller sphere here is Mercury's sphere, and it's inscribed inside an octahedron, which in turn is circumscribed by Venus's sphere. To say a sphere is inscribed inside a solid figure means that its surface just barely touches one and only one point on each of the sides of the solid. Meanwhile, the outer sphere touches each of the corners of the solid, but does not otherwise touch the solid. So all 3 figures have to be sized just so that these precise relationships hold. Let me quickly show you how he filled the remaining gaps. Here we see an icosahedron sandwiched between the spheres of Venus and Earth. Here we have a dodecahedron sandwich, a tetrahedron sandwich, and finally a cube sandwich. Now, Kepler did not just randomly assign each Platonic solid to each of these gaps. There was a method to his madness. Let me demonstrate by showing you 2 examples. It is a provable geometrical fact that for any icosahedron, the ratio of the radius of the circumscribed sphere to the inscribed sphere is approximately 1.3 to 1. Now this was very close to Kepler's estimate of the ratio between the radius of Venus's sphere to Earth's sphere, but he also knew that his estimates were just that. There was certainly a margin for error, so he could not be certain that the fit was perfect. And because God is perfect, he was looking for that perfect fit. Just to give you an idea, we now know that the ratio of Earth's average distance from the Sun to that of Venus is about 1.4 to 1, so very close. As another example, for any tetrahedron, the ratio of the radius of the circumscribed sphere to the inscribed sphere is about 3 to 1. In actuality, the ratio of Jupiter's average distance from the Sun to that of Mars is about 3.5 to 1. So again, Kepler, knowing that his own estimates were not precise, had high hopes that with better data he could show that the fit was perfect. He found similarly good matches for the remaining gaps using each of the 3 remaining Platonic solids. In any case, for each gap, there was one and only one Platonic solid that came close to providing a good fit. When Tycho died, Kepler took possession of Tycho's data. Naturally, armed with better data, he was eager to test his theory of the Platonic solids. He began with the orbit of Mars. Sadly for Kepler, it eventually became clear that Mars' orbit was not a perfect circle. To his credit, Kepler put aside his Platonic solids theory and went looking for an answer that fit the data. For example, at one point he considered an ovoid or egg-shaped orbit. I guess the Sun would be the yoke. That's an astronomy joke. But the joke, or the yoke, was on Kepler. He was wrong once again. But he didn't give up. And finally, he realized that the orbit of Mars was an ellipse. From this realization, he inferred that all planetary orbits were elliptical, with the Sun at one focus. This became Kepler's first law. Now, he also knew that the orbital speeds of the planets was not a constant. They move fastest when they are closest to the Sun, and slowest when they are farthest away from the Sun. After some trial and error, he discovered his second law, namely that planets sweep out equal areas in equal times. To be clear, planets cover different distances in equal times when they are at different points in their orbit, but the areas that they sweep out, as shown here, are equal. His third and final law correctly formulated that elusive relationship between the orbital period and the size of the ellipse. The square of the orbital period is proportional to the cube of the semi-major axis of the orbital ellipse. Now, all 3 of Kepler's laws are correct. The point also to remember here, though, is that he arrived at them by trial and error and inductive reasoning, starting with a set of data. Therefore, they can be considered empirical laws, but not fundamental universal physical laws. That's where Newton is going to come in. You might be wondering why I bothered to tell you about Kepler's theory of the Platonic solids. After all, not only was it wrong, but from our modern viewpoint, it seems ridiculous. Well, I told you about it because I think it makes an important point about how science works. Ideas that seem crazy usually turn out to be wrong, but not always. In order to discover the right path forward, you often have to try out a lot of wrong paths first. Remember what I said about science being self-correcting. You will only know that you are on the right path if the data fits your theory. Sometimes you already have the data you need, and other times someone needs to go and get better data. Consider this quote from Einstein. "Imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world, stimulating progress, giving birth to evolution. It is, strictly speaking, a real factor in scientific research.